In this video, we will learn how to solve second or higher order ordinary differential equation that is non-homogeneous and linear. This method will cover both cases, equations with the constant coefficients and those with the variable coefficients. To find the solution of these types of ordinary differential equations, we'll be using this general form. Here, y of c is the complementary function, which is the general solution of the associated homogeneous equation, and y of p is the particular solution of the non-homogeneous equation. We will find this and this separately, and eventually, we are going to write them together with a positive sign. Now let's take a look at how we are going to be finding the y of c. To find it, we first write the non-homogeneous equation in standard form. Assume that we are having this non-homogeneous equation where the r of x is not equal to 0, and it is having variable coefficients. Do note that this method is going to be used for solving both the non-homogeneous equation with constant coefficients and the variable coefficients. And here, I have taken the example of the variable coefficients. So first, you're going to be writing this non-homogeneous equation in standard form, meaning that you're going to be making the coefficient of the second derivative equals to 1. This is going to be done by dividing both sides of the equation by ax squared. Then, we are going to be equating the right-hand side of this equation equal to 0, which is going to be giving us the homogeneous version of this equation. After solving this homogeneous equation, we're going to get the general solution, which will be written in this form. The y1 and y2 here are the two linearly independent solutions of the homogeneous equation. Now, for the particular solution, we are going to be using this formula. Here, y of p is denoting the particular solution. u1x and u2x are the functions to be determined. And recently, we just found out the values of y1x and y2x in the general solution of the homogeneous part of this equation, y of c. To find the values of u1 and u2, we use Wronskian method. For that, we are going to be finding the Wronskian determinant, which is going to be denoted by W. And it is given by 2 by 2 matrix here. We can calculate two additional determinants, W1 and W2. W1 by replacing the first column of W with 0 and f of x, and W2 by replacing the second column with 0 and f of x. Here, f of x is a non-homogeneous part of this equation. Now that we have found the determinants, we are going to be using these formulas. For u1 prime, we'll be doing w1 divided by w. And for u2 prime, we'll be doing w2 divided by w, where the prime represents the first derivative of u1 and u2 respectively. After that, we are going to be integrating both sides of the equations for u1 and u2 both to find the value of u1. Eventually, we'll be substituting u1x and u2x back into their original equations for yp, particular solution. And finally write the complete solution as y is equal to y of c plus y of p.